So, welcome to the robotics reading group. I'm muting everybody. It is our absolute pleasure to have Stefanie Tellex from Brown here to give the talk at our reading group. She was supposed to come for real to the University of Montreal. We had her scheduled and everything, but then
I booked flights, and it was a bummer.
Everyone knows sort of the history, but it's really an honor to have her. Stefanie and I have known each other for quite a long time, since I was at MIT, and then we have a joint affinity for duckies and things like that. Plus, I don't know, I just like hanging out with Stefanie. I always learn so much from talking to her. So today she's going to talk about towards complex language in partially observed environments. If you have a question for her, just write it in the chat and I will interrupt her. Let's keep like questions during the talk as mostly points of clarification. And then I'll stop the recording at the end and we can have more expansive discussion about deeper issues. So with that, I'll let Stefanie take it away.
Cool. Thanks for the wonderful introduction, Liam, and it's a real pleasure to be here virtually, and I can only wish that I could be there physically, but someday. So this talk is called Towards Complex Language in Partially Observed Environments. And I'm Stefanie Tellex, as Liam said. I'm a professor at Brown, and also I work one day a week at Real-Time Robotics, which is a company based in Boston, founded by George Konidaris and others that works on motion planning accelerated hardware for industrial robots. So I think it is one of the most exciting times to be a roboticist. Technologies like this autonomous forklift, which I worked on when I was a postdoc at MIT in a project led by Seth Teller, have they already had a huge relevance in terms of leading towards self-driving cars, and companies like Waymo, where they're fielding cars without human drivers on the street. And now in the age of a global pandemic, this sort of technology has I think a really important role to play to create opportunities for social distancing, basically, and keeping people apart so that because robots can't get sick. There have been tremendous advances in drones. So this is a picture of our drone, the Pi drone. Now we call it the Ducky Sky drone. This is a Raspberry Pi Python autonomous drone. It costs about $225 in parts. And all of the autonomy on this platform is on board in Python, implemented in the Python programming language. And this project started after Duckytown. It was very much inspired by Duckytown in the idea of creating a flying platform that had many of the properties of the Duckytown ground platform in terms of being accessible, open source, and autonomous. And actually now we're merged with Duckytown. So this is the Ducky Sky drone. And I was just telling Liam that these just showed up in my lab. So these are $299. It was supposed to be $300, but somehow FedEx lost one package, so it's making its way. So it's going to be $300 when that last drone arrives. Drone kits that were sourced for us and made for us by Duckytown Engineering. And that we're going to be giving away over the next 2 years to high schools in Rhode Island and other places also. This is a shot of my drone class at Brown. It's weird to see this picture with all these people together, not social distancing. Of course, this was before COVID. But the idea, like Duckytown, is we taught a course. I created a course where each student gets their own autonomous drone. They put their drone together and then they learn how to program it in order to learn about autonomous robots and then take home a flying vehicle. And of course, commercial drones have seen a lot of advances as well. My favorite robot in the world right now is the Skydio drone, which is an autonomous drone with 13 cameras. And it can fly autonomously in outdoor environments and find people and follow people and collect video And we got SDK access. They might take it away, but we got it for a while anyway. And we can programmatically tell this drone what to do and where to go. So this is a pretty substantial and major advance when this platform came out compared to the state of the art, where you have to have a human pilot essentially making sure it doesn't hit stuff. So as robots become more powerful and more autonomous and more prevalent in our daily lives, there's a real question that we have to confront, which is how are we people going to interact with them and work with them and collaborate with them? The state-of-the-art interfaces for all of these robots, for the Waymo self-driving cars, for the Skydio drone, even for our drone and the Ducky drone, is some kind of other computer device. So in the case of the forklift, there was a tablet interface where you could circle the object you wanted the robot to pick up and then circle where you wanted to go. In the case of the Waymo cars, there's a tablet device in the back of the seat when you get in the car that you can use to control where it's going. And the same thing for the Skydio drone. There's a little app you install on your phone to tell it what to do. And these interfaces are good for applications where there's sort of a limited set of things you want the robot to do and where like point and click kind of makes sense. But the challenge with them is that the user's hands and eyes are down in the interface rather than out in the world where the robot is and where all the stuff that you care about is. So what I've been working on, what my research program is about, is trying to make interfaces where you interact with the robot as if you were talking to a person. So if you're working with a robotic forklift, you might say in words something like, put the metal crate on the truck. And then the robot has to figure out this mapping between the words metal crate and something that's out there, that it has to detect from extremely high dimensional sensor data coming in through its cameras and its LiDARs. And the sensor data, of course, is coming in at an extremely high frame rate, 30 hertz, 100 hertz, depending on the device. And the data doesn't always see the whole environment at the whole time, right? So a camera has a limited field of view. A LiDAR, might go out to 30 or 40 meters, but then it can't see beyond that. And somehow the robot has to make sense of this really high dimensional, noisy data that's limited and figure out the mapping between words like the metal crate and truck and stuff that's out there. And then it has to translate that into action. At the lowest level, these actions are also really high dimensional and coming out at a really high frame rate. You might be sending, joint commands to a robot arm at 100 hertz. And somehow sequencing these commands in order to cause the robot to do the thing you want it to do. It's also challenging because people don't like to stick to a fixed vocabulary and grammar. So this is a video that I've been showing for a really long time, but this is a forklift in simulation doing this little motion of picking up the pallet, driving forward, and putting it on the truck. And what we do, and we still do this, and all the time, since I've been showing this video for probably 10 years, but this is still our data collection paradigm, is we show people some representation of what the robot's doing. And then we say, how would you command an expert human operator to carry out the action in this video? What words would you use to tell a person to do what you're seeing this robot do? So we go to Amazon Mechanical Turk and we ask them, and they say things like, put the tire pallet on the trailer, which is kind of what we expected to get. But they also say things like, place the pallet of tires on the left side of the trailer, or lift tire pallet, move to unoccupied location on truck, lower tire pallet, reverse to starting location, lower forks, end. And actually, when we show this video to different people, we get a really large variety of different natural language commands. These are just some of the commands that we get. No two of these commands are the same. And they're all for that really short, relatively straightforward video, the robot driving forward a little bit, lifting up that pallet and putting it down on the truck. And the challenge here is that they're all kind of right. They're all a little different. They all capture different aspects of what the person wants the robot to do. And we want algorithms, we want computational frameworks that can take as input any of these commands and then output behavior where the robot goes and does the right thing. And of course, we don't want the robot to do just one command of putting the pallet on the truck. That's not what language is for. Language is really good because you can say all kinds of different things, you know, not just one kind of action. So you might say put the metal crate on the truck, but you might give a really low level command like move backwards 10 feet. Or you might tell your robot in your house, tilt the picture frame to the left just a little. Okay, stop there, good. And you want to understand these really fine-grained low-level commands. Or you might want to give a really high-level abstract command. You might say to the forklift, move everything from receiving to storage. I need more space in my warehouse. You might say to your home robot, clean my house, and go away and expect it to operate autonomously, come back later and have the job done. The power of human language and natural language is that you can really flexibly switch between these different levels, these really low-level, fine-grained commands and really abstract commands and anything in between at a moment's notice. And of course, this is a tremendous computational challenge because a person can talk about anything that that robot can do, and we want to be able to understand it. And finally, language isn't just about giving natural language commands, telling the robot what to do. Stuff goes wrong all the time in our robots, and stuff is definitely going to go wrong in our language understanding module for our robots. What we need is for the robot to have the ability to detect and then recover from these sorts of failures to understand. So if you say, put the metal crate on the truck and the robot doesn't understand, you'd like for it to come back with a question like which truck, to make targeted questions that collect information about exactly what the robot needs to know to continue operating autonomously and to successfully follow that natural language command. So this challenge of making robots that can understand language and that can interact with humans using language, I like to sum it up with the sentence: people want to talk to robots about everything they can see and everything they can do. Everything. And this is what makes language powerful as an interface, but it also makes it really challenging because the language understanding module, to really take on this problem and to take it seriously, has to connect to every single part of the robot's sensing and actuation system. So this is sort of the research problem my group has been thinking about. So the aim of my research program at Brown is to enable human-robot collaboration by learning decision theoretic models for communication, action, and perception. So the communication is about being able to talk to people, understand language, and have language outputs. The action, we need to have models of actions that the robot can take because people want to talk to the robot about everything it can do. So the language understanding model, the communication model, has to connect somehow to the action model. And perception, because people want to talk to robots about everything the robot can see. So we need some kind of model of what the robot can see, what it knows about right now, and also what it needs to look for, what it needs to pay attention to, and what it needs to ignore in order to efficiently find a policy, find an action sequence to follow the person's command, to do what it's told. So the idea is that by learning decision theoretic models for these things, we can scale to really large problems, because by learning, we can leverage large data sets that let the robot learn from those data sets. We don't have to hand program in the meanings of all of the words that we want to understand. By taking a decision theoretic approach, we're going to be able to detect and recover from failure, both failure to take and execute physical actions, if the robot tries to pick something up and drops it, but also failures to understand or to make itself understood. So the robot can ask questions when it gets confused. And then by combining these things together, the robot can improve from experience and get better over time. So concretely, the computational framework that my lab is working within is that of partially observable Markov decision processes, POMDPs. So I think most of this crowd probably knows POMDPs pretty well, considering it's UDM. And you have Joel, but I don't know.
Also McGill.
And McGill, yes.
But mostly you then.
Yeah. Did you say UDM or UDM? Sorry.
Say U de M.
UDM. Okay. UDM. Okay. So I'll just briefly go over POMDPs, and you can read that wonderful paper that it's cited below if you haven't seen them before. So basically, the idea of a POMDP is you have a Markov assumption about states. So each state depends only on the previous state and not on anything that happened before the previous state. At each state, you get to observe something about the environment. So here the shaded Z's mean these are the observations I get. I get to know what those are. I don't get to know what the state is. I also get to pick an action. And based on what action I picked at the previous state, that's going to affect what happens in the next state. So if I decide my action is going to be to pick something up, in the next state, maybe I'll be holding the object, or maybe I've dropped the object, but that fact that I tried to pick something up is going to predict something about what happens in the next state. And then finally, there's a notion of goal, the reward. So it's a cookie that I get, and the job or the problem of solving a POMDP is to find a policy, a sequence of actions, a sequence of mappings from states or belief states to actions that maximizes my reward over time. So POMDPs have a bad reputation because they're really, really hard to solve. In fact, they're undecidable in the general case. So sometimes people get worried about using them because of that intractability. The reason that we're thinking a lot about POMDPs for this problem is, despite being intractable, they're the simplest model I know of that captures everything that a robot is: an agent that can observe something about the world, that can take actions in the world, and is trying to have some kind of goal, this kind of reward function. The other thing I like to say is that POMDPs are like Python. So Python is a programming language. It's also undecidable, but that doesn't stop us from trying to write robot programs in Python. So the game is not just to say, oh, we're going to use Python. The question, or the research questions that arise once you commit to a framework like this are, what are the structures that we're going to use in order to enable efficient learning and inference, in order to enable this framework to solve these problems of understanding language? So what we're working towards in my group is something I call the human-robot collaborative POMDP, the specific POMDP with specific independent assumptions about the random variables, and also specific learned models. We're big fans of deep learning, that enable efficient learning and inference to handle these very general language problems. So the first thing that we're going to do to sort of step towards the human-robot collaborative POMDP is we're going to factor the state into two parts. We're going to say that there's the physical state of the world, so where the robot is and where the objects are that it might be interacting with. And then there's also the human's mental state. Most often we're modeling this as, what does the human want the robot to do? But something in the human's brain, we don't get to observe the human's mental state, but we're going to reason about it. But we are going to try to sort of figure out like what the person wants. So this is going to let us rewrite our reward function to say, well, do what the person wants. We don't know what it is, so we got to figure it out. And then once we figured it out, then we try to find actions that cause it to happen. How are we going to figure it out? Well, we're going to take our observation model and factor it into physical sensor observations. So this is all of your standard robot sensing modalities, cameras and LiDARs and stuff. And then we'll separate out language, human language, and human gesture. And these are the modalities that are going to allow us to make inferences about what the human's mental state is, what it is that the human wants. So then we can think about different subparts of this model and study them individually. So this problem of looking at human language input and trying to estimate the human mental state, what does the human want? This is the problem of language understanding. And I'm really, really happy to learn models, deep learning models. And in fact, Dilip, who's here, my former student, spent a lot of time making deep learning models to try to learn to predict human mental state from natural language input. This is the problem of human language understanding. Then you can think about actions the robot can take that don't not only change the physical world, but also actions, communicative actions that try to change the human's mental state. So the idea is by taking an action like asking a question, you're changing the human's mental state in a way that will hopefully cause the person to answer the question that you asked and get you the information you need to go off and do the thing that you're trying to do. And that's sort of what I call those parts of the POMDP, or what I think of as communication for collaboration. Then you could think about actions. So in the sort of classic POMDP model, there's like a flat action space. There's just a big old list of actions the robot can take. But the challenge here, the problem with that approach, is that the space of actions the robot can take is really, really big, and it's really hard to search in a space where the space of possible actions is so large. So we're going to need models and representations that allow the robot to reason about hierarchical spaces of actions. And this is going to allow the solving the POMDP to go much faster. And it's also going to make for a more natural mapping between what different goals the person might have and ways that the robot is going to achieve those goals. And so that's what I think of as, and figuring out like what that space of hierarchical abstract actions looks like. How can you learn it? And how can you fit it into a coherent representation so you can connect it to language, is what I think of as action for collaboration. And then last of all, there's this problem of estimating the physical state of the world from our sensor information. And this is sort of classic robotics like SLAM and those sorts of problems. The thing is, when you bring in language, what you really quickly see is that there's problems that are really easy to describe in language that have to have a lot of input or in terms of how the perceptual system of the robot's going to work. So one of those examples I like to call the speck of dust problem. You tell the robot, there's a speck of dust on the floor over there, pick it up and throw it away. Before I mentioned the speck of dust to the robot, it really better not have been tracking every single speck of dust on the floor, right? Because it's clearly computationally intractable to be paying attention to every speck of dust on the floor all the time. But as soon as I said those words to the robot, and I gave it this goal of finding the speck of dust, picking it up and throwing it away, the speck of dust better be just about the most important thing in the robot's mind, right? Like it better really be focusing on finding the speck of dust, brewing up a speck of dust detector, aiming it all around and trying to find it so that it can pick up the object and throw it away. So this is an example that kind of shows how language is really integrally tied with the perceptual system, and we need to figure out ways of making that connection happen so that we can understand those sorts of commands. And that's what I think of as perception for collaboration. So my group is thinking and doing research in all three of these areas, and we have papers in all of them. But I guess I'll start with the communication thing, because for me, it's really motivated by language. And I like to talk about this work that we had at ICRA a couple years ago, because it kind of shows how all of these pieces come together in a relatively simple model that I think is still pretty interesting. So the idea here is the robot is trying to deliver an object to the person. And I think that this is a really nice problem, because object delivery is kind of the beginning of everything you want the robot to do. Like the first thing you have to, for many, many different tasks, from emptying the dishwasher to cooking to doing laundry, the first thing you got to do is get your hands on the right object. You might have to do more stuff after that, but first you got to pick it up. So the idea here is the person wants the robot to deliver an object, and they're using language and gesture to say which object they want, and the robot's got to figure out which one it should hand over. So they might say something like, "Can I have that bowl?" and they point. And then the robot is going to maintain a belief distribution over which object it thinks the person is talking about. And here in the system, we used really straightforward keyword-based language model, a generative model for pointing that said you point at the thing that you want. And if you use those models and you run standard, Bayes filter kinds of inference, what you get is a belief update where in this sort of situation, the robot very quickly decides you want bowl number 2 and hands it over. But then what we did is we made the problem harder. We moved the person back. We rearranged the objects so that we put like objects next to each other. And the person says, "Can I have the marker?" And they point. And now it's more ambiguous. So the same sort of situation, but what we get is a distribution where it's confused between which of the two markers you're supposed to hand over. So now the question is, what should the robot do? We don't just want to pick randomly and hand over an object, because we're going to be wrong half the time. So what we'd like is for some way for the robot to decide that it needs to ask a question, and also decide what question to ask in order to disambiguate the situation. So what we did to solve this problem is we defined a POMDP model. We called it the fetch POMDP, and I won't get into all the details, but the basic idea is it has to reason about whether it has enough certainty to hand over the object, or whether it doesn't, and then it should spend time and energy and incur a cost to ask a question to disambiguate what's going on. We called it the fetch POMDP. And what this lets the robot do is reason about which question it should ask. So it points to one of the objects it's confused about and says, "This one." The person says, "No, not that one." They say no. And then we can update from that and figure out the correct object to hand over. And then it hands it off. So I'm going to show a video of what this looks like running on one of our robots. Oh, I cut the video. Sorry. I usually show a video, but I skipped it. So I guess you'll miss the video. That's, and I cut it because I was giving this talk last time over Zoom, but then I figured out how to do Zoom video transmission and turned it on, but I guess it's too late. It's gone. So there's a video. It's cool. It's cool because it's fast. The robot really quickly makes these inferences and then, hands over the object, or really quickly asks its questions. And we had a user study where people came in and talked to the robot. It was a within subjects design. So each subject got to try 3 different interfaces where the robot never asked a question. It just made its best guess about which object you're talking about. Or it always asked a question. So no matter what, it always asked a disambiguating question. Or intelligently asked a question. And then we measured the speed of the interaction and the accuracy of the interaction. So that the idea is to see which interface is fast and accurate. And we found that our question asking interface was 25% faster and more accurate than an average of the baselines. this really surprised us because we thought if you always asked a question, like it wouldn't hurt and it might be slower, but it would only help. But what we found was that asking too many questions just confuses people. So it actually cost us an accuracy. The robot did worse if it asked a question when it didn't need to, than if it just, picked the right object. The other really interesting thing is that almost 40% of our users, when we asked them, thought the system could understand prepositional phrases like to the left of. And here we were using just a keyword language model where each object had a bunch of words that we manually put in that could describe it. There was no spatial language at all, even though I love spatial language and we're working on it now. But there was no spatial language in this system at all. And yet the question asking gesture interface was so smooth that it gave the illusion for many of our users that the robot actually was understanding these sorts of commands. So that piece of work is one example of taking this kind of POMDP approach. And I like to start with it because it kind of puts the pieces together, even though it's a relatively simple and well-defined task. So now I'm going to talk about some of the work that Dilip worked on, where we focus on the problem of understanding language, and we think about understanding commands at these different levels of abstraction. So the challenge here is how can we represent the action space of the robot? So we're going to move to study this problem in a grid world formulation that we call cleanup world. And the idea is that the robot is moving around in an environment. Each object and the robot itself could be in one of these grid cells. And we're going to switch to an MDP setting just to try to make to focus on like the language and action pieces of this. So here we're going to assume that the natural language command defines the reward function of the MDP, and we're not going to think at all about any uncertainty over that. We're just going to try to make a model that goes from English to the reward function. We assume it's right, and then we go and find a policy that maximizes that reward function. And the challenge in this kind of cleanup problem is you'd like to give really fine-grained commands, something like go down 5, right 5, 1 up, right 4, down 1, left 1, and up 3. Or you'd like to give a more abstract command, like take the red chair to the blue room. And if you actually follow the lower level sequence on the left side, it turns out to be the same thing. It'll push the red chair into the blue room. But the thing to sort of take note is that there's situations where you really like to give fine-grained commands. So like if you're only allowed to give abstract commands, you can't say something coarse-grained to the robot like move north. But on the other hand, if you're only allowed to give really low-level commands and you try to scale to a larger environment, so this is one fun large environment, the International Space Station, then the person is stuck giving really low-level commands, and they almost might as well be teleoperating the robot with a joystick. We really want a model that can understand both sorts of commands. So in prior work in this area was at RSS a bunch of years ago, where you learned a model that maps from the natural language command to a, thanks Liam. Liam's showing his RSS shirt if you're not watching.
It's the 2015 shirt too. It's the
2015 shirt. See, see, I changed out of my t-shirt and put on like I don't know if you can see my nice robot shirt. There's like little robots on it. My professional robot shirt for this. All right, so yeah, so this was at RSS in 2015. It was cool because this paper actually, this 2015 paper was neat because previous work for mapping between English natural language commands and making the robot do stuff mapped directly from language to action sequences. This was the first paper that mapped from language to reward functions, to goals, to try to really capture what the person wanted the robot to do. And what you got by doing that was having the ability to recover from failure, because you had a goal representation. So if an action fail to execute and you only had the action sequence, then you're stuck. But if you have a goal representation, then you can recover from failure. And so this was the first paper that I'm aware of that really said we're gonna go map from language to reward functions to goals. But it was a flat space of possible reward functions. So what we did instead is said, well, we're not gonna do language to a flat space of reward functions. We're gonna have different levels of abstraction, and we're gonna try to predict from the language both the reward function and also the level of abstraction that the robot is talking about. And one of the authors of this paper is actually here. So hi, Dilip. I was talking to you before, and I mentioned him. He's my undergraduate student. Now he's a PhD student at Stanford. And the idea here was that we could then understand natural language commands at these different levels of abstraction. So we changed to a hierarchical action representation. Now for this paper, we manually specified the action representation, but we don't really think that's right. We want to learn it. And we had a paper at Coral last year where we were learning abstract models that could predict the state of an object like a microwave that had never seen before. It could predict how open or closed the door was given a point cloud of the microwave, and then use that model to like plan to open or close the microwave. And we learned this model with deep learning. So I don't want you to think that just because I'm talking a lot about POMDPs and Bayesian generative models that I reject deep learning. I actually think that they're really closely tied together. And part of the game that we're playing is to say, like, what structures can we put in the model? And what stuff should we learn in order to get this compositional behavior that we're looking for?
Go to the red room.
So here's a video of it running. You should say something low level, like go to the red room. And it does it. And here the rooms are marked with tape.
Go south, south, south.
You can say high level or you can say low level, go south, south, south. And you don't have to change the robotic system in any way. In between the language understanding system, it's able to figure out what level of abstraction you're talking about and execute the command. So that's sort of one class of abstraction that we were able to handle. Then we got really interested in a different kind of abstraction, and this was what we called non-Markov commands. So the idea is that people all the time say things like go through the yellow room to the blue room, where they describe the goal, where you want the robot to end up in the blue room, but they also describe how you want the robot to get to the goal, the path that it's going to take to get there. And at first glance, it seems like it's sort of mixing up reward functions, you know, the goal that you're trying to achieve, but also actions, like you're supposed to take an action that moves you through the yellow room. But what we realized is that these sorts of commands can actually all be expressed as a goal-based command. It's just that the goal is it's a non-Markov expression in the usual state representation of the robot, where in a sort of typical, you know, MDP or POMDP defined for a robot like this ground robot here, the state is the current position, not the whole history of previous states. And if your state is the current position, and you don't have access to the history, you can't evaluate if you've been through the yellow room or not. You don't know the answer to that question. If you saved the whole previous states in your state, then you could evaluate that. But then you have a computational intractability problem because you're saving the entire possible history. It gigantically blows up your state space, and it gives you big problems. So what we realized is that there's a formal specification for these sorts of constraints called linear temporal logic, LTL. This is used a lot in the programming languages and model checking communities, and it's also used in robotics. There's a formal methods community where the input is an LTL specification, and the output is a policy, a provably correct policy for the robot that is guaranteed to be correct, assuming unrealistic things. So LTL is a generalization of first order logic, where it adds these temporal operators. So finally, P, some proposition, means that finally at the end, some proposition has to be true. Globally, P means it has to be true for the entire time. Next is like it has to be true at the next state. And P until Q means P has to be true until some other thing Q is true. So these LTL expressions allow you to have predicates and actually have goals that you want to be true over the sequence of states of an MDP. So the approach that we took to solve this problem is to represent the problem with a Markov decision process, a sort of traditional one where the state was only the robot's current state. We call that the environment MDP. And then you convert the LTL expression into I think I had a slide for this, and then you convert the LTL expression into a finite state automata. And this is a second MDP, which we call the specification MDP. And then you basically glomp them together. You collide them at high speed to get this merged MDP. And the special thing about the merged MDP is that it contains these extra variables, these extra state variables in the specification MDP are basically giving the environment MDP just enough extra memory to evaluate the LTL expression. So it's basically adding just enough extra stuff to say whether or not I've ever been in the yellow room, if that was what I was trying to do. So that adds just enough extra state for that particular command to be evaluated, that particular LTL expression to be evaluated, but not the whole possible history of possible previous states, so that you couldn't evaluate any possible LTL expression, only that one. And then you find a policy that satisfies this merged MDP, and it's Markov and everything is happy. And what this allows us to do is understand natural language commands like go through the yellow room to the blue room, or avoid the yellow room and go into the blue room. And Dilip wrote this paper too. Here's the video.
Go to the blue room.
So here the default path was to go through the green room.
Avoid the green room and go to the blue room.
So now he says avoid the green room and go to the blue room.
Go through the yellow room to the blue room.
We speed up our video because our turns are slow. Okay. So then, and I won't go into this paper in detail, but we talked about sort of action abstraction and we talked about temporal abstraction. We had a paper at RSS last year that combined these two types of abstractions together so that you could follow commands that involved both non-Markov elements, but also different levels of abstraction at the same time. And there was some tricks we had to play to make that work, which I'm skipping. And now I'm pretty excited because what we have is like a pretty general system for understanding a pretty wide variety of natural language commands with abstraction and with these sort of non-Markov elements that seem to show up a lot. So what we did is we started trying to make this work in more realistic environments. So this is showing a model of a drone flying around in an OpenStreetMap environment in, I guess, I don't actually know where this particular spot is, but we're working in lots of different, environments for which we have OpenStreetMap data. So that means because we have the OpenStreetMap data, we know a lot about landmarks that the person might refer to, because these are all in the map. The buildings and stuff and their names and the street names and the like are all in the map. But what we realized is that there's a problem. In all of our previous work, we kind of had a closed space of landmarks. There was the red room, there was the green room, and if we had never seen the purple room at training time, we would never be able to do the purple room. But what we wanted for this sort of OpenStreetMap setting is to be able to unbox our drone and take it to any city for which we had OpenStreetMap data and say things like fly to the big blue bear. At Brown, we have this weird sculpture of the big blue bear with a lampshade that like half goes through its head. And we'd like to be able to say to the drone, fly to the big blue bear. It's a great landmark. It's really unambiguous and really striking. It stands out in your mind. It's in OpenStreetMap. It's labeled with words like blue and bear. And we'd really like to be able to have the drone follow these sorts of commands. So here's the bear. You can see it. The lampshade goes through its head. It's kind of weird. So to handle this, we created a system where you have the natural language input, and then we used a deep learning approach from the NLP community called CopyNet, where you recognize that the phrase, the medicine store here, is a referring expression that maps to something, and then you kind of pull it out as a function. So there's some function, you're supposed to finally be at the medicine store. And the CopyNet part takes the exact string, the medicine store, from the input and puts it as the input to this function. And then the implementation of this LM function is a landmark resolution module, where we take those words, the medicine store, and we take the OpenStreetMap database, and based on where we are, we filter it out, and we figure out that CVS and Walgreens are likely things that they could be talking about. And what this enabled us to do is, and we had a little user evaluation, is to have people, without being scripted on what the robot could or couldn't say, could come to and go to simulated Tulsa, Oklahoma, and start giving natural language commands to the drone and have it work, even though it's never been trained in the city of Tulsa, Oklahoma before. So the last piece, let me see what time it is. The last piece of work I'll talk about just got accepted to RSS. It's going to be presented next week. And what I kind of glossed over with all of the papers I've talked about so far is that for every single one, we had to create a data set of English commands. We usually work in English, although in principle, it would work in other languages. Who knows in practice? But anyway, in principle, so we collected a data set of natural language commands paired with some representation of the meanings of those commands. And what that means is that we had to do lots of annoying annotation and correction and battling with our annotator, not really battling with them, but like it would be things like, we would write for our non-Markov command, we would write things like, we would show them a video of the robot going through the yellow room and avoiding the blue room. And then we would annotate that with an LTL expression for avoid. And they would say it's, go through the blue room and not the avoid expression we were looking for. So we would get examples of language paired with the wrong expression. Then Dillip, because Dillip was the one on this paper, poor Dillip had to go and manually generate, manually correct these sorts of examples. And what it meant is that the data sets that we're looking at, and all of the work that I've told you about, is in the size of hundreds or at most 1,000. The LTL work that we've done was the largest data set of English to LTL published to date, and it was a few hundred examples. And if you compare this sort of data set to existing work in the NLP community, for example, in the machine translation community, they're looking at parallel data sets of human language pairs I often use the example of the data sets from Canada because the Canadian government records are published in both French and English. So it's one of the data sets used for this. It's a parallel data set of with the same meaning translated into 2 different languages. And they use large data sets of these parallel corpora to the tune of millions. And things work a lot better when you have millions. But it was always prohibitively expensive for us to create that because there's no data set of millions of robot ease expressions. So what we've done is created a learning algorithm that is able to learn from parallel data of English sentences and trajectories of the robot doing something, robot behavior that's labeled as correct or incorrect. So here the natural language instruction is walk along 3rd Street until the intersection with Main Street, then walk until you reach the Charles River. And then we show 2 trajectories, one is correct and one is incorrect. And this data is really easy. The parallel data set of natural language instruction and trajectories is really easy and really reliable to collect from people on AMT. They can look at the trajectory, they can describe the language, we can be confident the language maps to the trajectory. It's that LTL thing in the middle that's really hard to collect from the Turkers. So what we did in this paper is we created a learning algorithm that is able to learn only from language and trajectories, and it's able to predict the LTL expression during training. So we're still using a goal-based representation. We're still able to detect and recover from failures because of that, but we don't need to have those annotations provided at training time in order to learn that. And what this let us do is scale to larger data sets than we've been able to use before. And it let us not have to annotate these LTL expressions. And this is going to be presented, like I said, next week or 2 weeks, whatever RSS is, at the most recent RSS. In collaboration, Roma Patel is a PhD student who's the first author, and Ellie Pavlik. I think it's, I'm super excited because not having to annotate and letting us go big data set wise is a really big deal. Okay, so I'm gonna skip over our work on finding objects, but we're thinking a lot about object search. So the idea that the robot is told things like find the mug in the library, the living room, and the kitchen, and then we have a POMDP model with a fan-shaped sensor. And the robot is combining information from language, but also information from its sensor data to find a policy, to find the object. My favorite thing about this paper is that it handles lying. So if the person says to the robot, you know, it's in the kitchen, then the robot will go in the kitchen and then look in the kitchen until it finds the object and everything is happy. If the person says to the robot, it's in the kitchen, they say it's in the kitchen, but really it's not in the kitchen. They lied to the robot. What the robot does is goes to the kitchen and then looks around in the kitchen and doesn't find the object. And then there's like a little smoothing term and it does its POMDP update and it's like, oh, okay, it's not in the kitchen. And then it goes and looks everywhere else until it finds the object. So it still finds the object, it just takes longer when the human lies to it. And if you're a POMDP person, this isn't surprising. This is the POMDP doing what POMDPs do if you set the problem up right. What was new about this paper was that we created a kind of a realistically large grid world setting, and we created a new kind of a POMDP, an object-oriented POMDP, that enabled us to efficiently find policies to solve this sort of problem faster than baselines. And we made it run on a real robot. So I won't show the video, but yeah. Okay, so we started out with a sort of spare POMDP model, but as we kind of go through each of these different pieces of the puzzle, our human-robot collaborative POMDP gets more complicated and more sophisticated. We're putting more structure in. We're also learning more things about the framework. And what we're trying to do, our end goal, is to create autonomous, capable, collaborative robots that can collaborate with people. And I'll just finish with this. It's not super related to POMDPs, but it is really cool. This is a paper where the robot is learning to write and draw. So we have a model that can look at a piece of handwritten text that it's never seen before. And here in all of these little examples, it's written in the top half by a human. And then only from the image of the text seen with its camera, it can find a policy for drawing the text with a marker. And we're doing it in a bunch of different languages. This was at ICRA last year. So I'll stop there. Thank you.
This is great stuff, Stephanie. If there's any questions, I don't know, people can just like unmute and talk. I had like one kind of small nitty question.
Mm-hmm.
So in your POMDP model, you make it look like gestures and language are treated independently,
Mm-hmm.
but then at least in the first experiment, it wasn't like clear to me how that could be so. If you're like
Well,
sometimes
what
it
they
would seem
are
like,
is conditionally independent given the state.
okay,
So they're not independent if you don't know what the person wants. But if you do know what object they want, then we assume they're conditionally independent given that information. So what that says is if I know that you want this object over here, then I can predict your gesture and I can predict your language, and they're separate. Which is probably not true. Like probably you would change your gesture or something depending on what, how you decided to express it, but it's not crazy either. Our gesture model basically says our gesture model doesn't need to think about language, and our language model doesn't need to think about gesture. I can predict what words you're going to use to describe it without thinking about what gestures you're using, and I can predict what gesture you'd use. Basically where you'd point, based only on its spatial location, not based on what words I use to describe it.
but that does seem like a design decision. Like you could have chose to jointly put those two things together, and you might have had better performance jointly than each of them independently.
Maybe. Maybe, yeah. I sort of feel like in the general case, you'd probably want to learn, a joint model for both. But it works surprisingly well to the conditionally independent thing.
Yeah.
The conditional is important.
Yeah, for sure.
But like, yeah, it works surprisingly well. And the model is very elegant because it's like this pointed gesture, and you shoot an arrow down, and it's Gaussian, and I don't know. I liked it because and then the language model was a little multinomial, and it was just like it really it was a Bayes filter, for doing those updates. It's very analogous to how SLAM is set up, for example. And I think the analogy there is like fast SLAM was all right, like made those assumptions that were strong, and that was all right. But then more sophisticated SLAMs don't make those assumptions; they weaken them, and they do better. But fast SLAM is still good, you know.
Makes sense.
Yeah.
Greg has a question.
I can ask it. I can ask it in oral form.
Yeah.
And by the way, I have my RSS 2011 T-shirt.
Nice.
Because I actually mentioned a piece of work from 2011. So you mentioned lying.
But you went and got it. You went and you just went and changed, right? Just to be clear.
No. I printed it. I haven't printed mine. Yeah, I went and changed. So glad you're having the camera off. Guess how many RSS T-shirts I have, by the way. Anyhow, my question is, you mentioned lying, and maybe that was just color, but lying has a lot of. There's a question of intent and consistency, and a bunch of things besides just noise, because otherwise lying could just be considered kind of noise in the interpretation process.
Yeah, so what I liked about it, like we definitely, in this paper, we didn't get into any of that at all. The sense in which we were able to handle lying is by treating it as a noise model with a smoothing term. So we assumed that the person was correct most of the time when they talked to us, but there's a small probability that they were lying, that they were wrong, whether that was lying or not. And we just pumped that through the POMDP model.
Yeah, so calling it lying is really cool, but I think, especially in the current political climate, it's worth being aware that lying actually is more than just making a little mistake.
Yeah, I agree with you.
So in proper POMDP modeling, if someone said something like, I think it's in the kitchen, then you would change your update rule for that?
Yeah, so in this paper, you know, in this particular paper was more about the POMDP model itself and less about the language. So the language model, again, was dead simple keywords, not learned, you know, with just a smoothing term here. But in general, and actually now we're working on trying to learn a language model. We're thinking about spatial language, which is what I did my PhD thesis on and then haven't thought about for a long time. So that you can say things like you know, find the car behind the building, and the behind should give you more targeted information than just, you know, that it's somewhere near the building or something like that. And such a learned model might learn to hedge more. So if you say, I think, if you sound unsure, then you would hope that a model could learn to say like, okay, I'm gonna up the probability that your information isn't gonna be correct, or that my interpretation of what you're saying isn't right.
I had a more general question.
Yeah.
So like there's a lot of people at NILA in Montreal who work on NLP.
Mm-hmm.
And I think it's one of the real areas of strength of NILA. But so for you, thinking about like NLP through the lens of a roboticist,
Yeah.
like what are the pieces or the particularities of the robotics problem in terms of doing NLP? Like for sure, like object grounding, like what you did in your PhD would be like one thing because there's a connection to the physical world. But like, how do you look at it differently than just a general NLP person? Because
Yeah. Yeah. I think what's different is kind of taking this framework that perception and action have to be integrally tied with the language. You know, the language speaking is a kind of an action. You know, language acts is something from philosophy of language. And hearing language is a kind of perception. So I think what's challenging about that for the NLP community is that it's hard for us like they want us to give them a data set or something. But we roboticists, like we don't have an agreement, or you know, or you know, we haven't converged on what robot ease really is even, you know. So like what the NLP people I think would love is a data set from English to robot ease. But we roboticists don't even know what robot ease really is. And I see, you know, one way of how I see my research program is like, you know, the abstraction and the LTL is like we're throwing different stuff at the wall to see what sticks, you know, hoping to converge on something that can be robot ease, that can connect, that can capture semantically what humans say in language, but that can really connect to our robot models like SLAM and Bayes filters and the like, and have information come wherever it comes. You know, if you told me, that's great. If I saw it with my sensor, that's great. But both of those things are changing my belief state, and I'm going to go make different actions based on what I believe to be true about the world. And that's hard because, you know, a lot of the work that we do ends up not being language work at all. Like a lot of times our language models are just not the contribution. Even when we're doing like a deep learned model, it's often a seek to seek deep learned thing off the shelf, you know, or we're taking CopyNet. We didn't make CopyNet, we took CopyNet. But we're putting it in this context of the robots making decisions, and it's got to, you know, it's got to make it run in a planning framework so it can actually, you know, execute the thing that you're supposed to do. Many of our papers look like planning papers. So like this particular paper had a tiny language piece, but the contribution here was a planning model, object-oriented POMDPs, and not a language contribution at all. But then once you had the planning thing, you know, trivial language stuff could be bolted on, and you got a substantial increase in the ability to understand a new kind of command.
I think Florian has a question. He's a postdoc.
Yeah. Hey, can you guys hear me?
Yep.
Yeah.
Perfect. So Liam literally just took my good question. So now I'm only left with a like tiny nitpicky question. So I noticed earlier when you showed the turtle bot like navigating around, like go through the yellow room to the blue room.
Yeah.
I noticed that like for like 3 out of the 4 demos, it worked pretty well. Like it immediately did the thing, and for the 4th one, it hesitated, and then you sped up the video 4 times. I was just wondering, like, what was happening there under the hood? Like, is there any particular part of this algorithm that's like slowing you down in practice?
I don't know.
Okay.
Dilip might know. But yeah, I don't actually know what was going on, why that one slowed down.
Okay. But like in practice, like there's no like other limitation you can think of on top of your head that would like cause such a thing.
No, typically the inference in terms of time, typically going from language to the formal representation of language is relatively fast. Going from the formal representation to a policy that we can go and execute, that's solving the POMDP or the MDP, is slower. And that's the thing that we're trying to make fast enough to run in real time. And depending on the study and the situation, we might not even care if it's much slower than real time. So like for that particular paper, we had a quantitative evaluation on a data set that we really primarily used to show how how well it worked, and then we just demonstrated it in video, and we didn't put much time to see how fast it would go, if that makes sense.
Okay, but like without a lot of optimization, like what's the order of magnitude of inference time there?
Seconds to minute or two.
Okay.
For most of our models. I'm sorry I cut the video. I mean, the very first one, the paper I talked about, the question asking one, was quite fast.
Yeah.
And we had to do some caching to make that happen. And it just depends on this. Like for dialogue, you've got to be fast. A lot of times when we're pushing the envelope for the semantic model, I wouldn't complain if it took longer, like 10 or 15 minutes even in the data set, although it's usually less.
Cool, thanks.
I have a question.
Yeah, please.
Who are you?
By the way, my question is about collecting the paired data of natural language commands and trajectories. I would like to hear in more detail, if possible, how do you collect these?
Yeah, so it does vary by the project that we're doing, but I'll go back to one of our papers. We basically give the user some representation of what the robot is supposed to do, and in this example, not do. So the blue arrows are like what we want the robot to do, the red arrows what we don't want the robot to do, and then we ask them to write down instructions that they would give to a human to have them do the thing, the blue arrow, and also not do the red arrow.
How do you solve the problem that you mentioned about avoid, that like sometimes you would like...
Yeah, so in the case of the LTL paper, I think we have a data set slide for that one. We manually relabeled the LTL expression. So they would, we wanted them to say, avoid the yellow room, and we would annotate an LTL expression with, never be in the yellow room. And then the idea is that they would say language, we would specify the LTL, they would only see a picture of the robot doing and not doing, stuff. But they would prefer to say go through the blue room. And we just fixed it by hand. So we would be like, oh, this one was go through the blue room, whereby we, I mean Dilip. So I hope he's still here. So we would just manually correct it, right? And that's what limited us to the size, in terms of the size, is that it had to be a small enough data set that we could do that. But in this particular work, the LTL expression is not needed at training time. So if they said avoid, if one person said avoid and another person said go through, the training algorithm will learn on its own with no supervision. It'll learn and to map the first sentence to avoid and the second to an LTL expression with avoid, and the second to an LTL expression with until. I shouldn't say no supervision. It's given a model of LTL. It's given the ability to evaluate whether a trajectory satisfies or not a particular LTL expression. So it's basically progressing it has a bunch of candidate at training time. It has a bunch of candidate automatically generated LTL expressions, and it progresses them through the trajectories that are provided as annotations, and then it it uses as supervision whether or not the expression is being satisfied or not. Does that make sense?
Yeah. All right. I guess it does. I guess I just didn't see. So what if people just do not say avoid? Never,
Well,
like,
in this case, they could say, like, they could say avoid, and they could not say avoid. They could say go through.
no, yeah. Well,
And
I mean,
there's
it's
no
just,
LTL expression at training time. They both map to the trajectories that are provided, and it'll learn different LTL expressions that go with those trajectories. So in the
okay.
one case, it'll learn avoid. The other case, it'll learn go through.
I think I've used all my question time. So thanks.
Okay. The paper is coming out like next week at RSS, so there's more detail there. But you know, if nothing else, take away that it doesn't have that problem. It doesn't need to be annotated. It can learn without that.
Hi, Stefanie. Hi. I have a question.
Yeah.
Thanks for the great talk. My name is Brendan. I'm wondering if you've thought about how to incorporate knowledge at all, some prior trajectories maybe, or through some knowledge base to condition the logical forms, the generation of these, and selection, so that you can prioritize those that are more plausible to try to, or do you think of this more as the source of truth is the language model that you fed it, and
a lot of so we haven't done stuff with, like, you know, ConceptNet or the like. A lot of the like basically all the work we've done to date with this is about, you know, trajectory following. You know, we're thinking about language in urban environments where it's not like you're trying to cook or something like that, where there's like information that might come from a knowledge base. The closest that gets at that, it maybe is this paper where we were trying to do landmark resolution, where the knowledge base was coming in the form of the structured OpenStreetMap data, you know, telling us what landmarks were out there and telling us also what words people use to describe those landmarks, so that we could have a learned model that mapped between noun phrases people would use in commands that they may have never seen before, and you know, objects that we could connect to the OpenStreetMap environment.
I see. So the language model really doesn't have any concept of the affordances of the agent, or did you? Is that something that you feel like could be pushed further into the language model?
Yeah, for us that goes into the planning model. So what we've thought about is having, given the expression for the reward function, given the logical, the goal, the expression for the goal, that should sort of translate back into algorithms for planning that may take that information into account, because you're trying to achieve that goal. So for example, based on, you know, what abstract space, you might have different abstract space of actions, and based on the goal that you're trying to achieve, you might, you know, search in some and not in others, for example.
I see, makes sense. Thank you.
Any last questions or thoughts? Awesome. Dimitri, you want one more kick at it? Dimitri, come on. Let's let Dimitri talk again. Ask your question.
Yes, I was just wanted. So I'll try. Thanks for giving me another shot. What I try to say is that when I'm using the robot and I have like a particular idea what it should avoid or where it should go through, then I'll say that. I might be very specific at expressing what exactly I want. But if I'm just given the trajectory of drone flying someplace, I'll say something not super precise, and there might be a mismatch between training and test data. So what are
Yeah,
your
so we
thoughts
would
about
show, this is an example of what we would show them, this slide here. So we would show them a correct trajectory and an incorrect trajectory to try to elicit that, you know, the sorts of commands that you're saying.
Oh, now I get it.
Does that make sense?
Thanks. Now
So
I
we
get
would
it.
we would try to elicit that.
You
And it's
listed them to be
definitely, though,
specific.
that's definitely as we try to study more complicated commands, we're finding ourselves in this dance of like trying to get more creative about how we elicit those commands in the first place. And then there's this question of like, did the way, I mean, of course, the way that we elicited the commands from them may not be representative of what you'd actually say or what, you know, the actual use cases are for a drone operating in the wild. So that's definitely a limitation of this approach, is that we're always trying to think of, you know, we are deciding, you know, we decided we were interested in these sorts of commands with avoids and stuff. And so then we went to Turk and elicited such commands from them using a particular methodology where we showed them positive and negative examples. And we iterated several times to get that to work. You know, we would get some hits, we'd look at it and be like, this is not very specific, we don't like it. And we'd give more detailed instructions and stuff till we got commands that we liked, and then scale it up.
Thanks. Now
Yeah.
I see. Thanks.
Cool.
Awesome. Stefanie, thanks so much for doing this.
Yeah, thanks for having me.
This is fantastic. Yeah, we're gonna put you on the internet so that everyone can see you.
Awesome.
But yeah, so maybe just like a virtual round of applause for Stefanie. And thanks everyone.
Thanks.
Thanks everyone for joining, and we'll see you next week.
Hey Tim, how are you? Do you want to?
Hey, how's it going?
I got your email.
Yeah, it's good to see you. Yeah.
Yeah, it's good to see you too.
Yeah. Great work as well. Thanks.
Yeah, how have you been? You want to drop into a breakout room or something, or?
Yeah, maybe we should chat. We should, chat in our own session.
Super.
Yeah.
Cool.
Here, I'll send you a link.
Okay.
All right.
Super.
Yeah. Bye-bye.
Ciao.